Okay, great. Thank you. Good morning, everyone. My name is Mark Maloney. I'm the Public Works Director for the City of Shoreview. I'm also the Chair of the CTS's Transportation Infrastructure Research Council. And just welcome to this meeting, this webinar meeting. I'm going to invite our Vice Chair of the Infrastructure, Christy.
Thank you, Mark. Hi, I'm Christy Mortar. I work for Hennepin County in the Transportation Operations Department, and I lead the Asset Management Division. And I've been the co-chair for this Infrastructure Council for a little over a year now.
CTS councils provide a forum for transportation professionals and researchers to exchange information on current transportation issues and trends. They bring together university faculty and staff with practitioners from the public and private sectors to recommend direction and participate in improving the center's research, education, and engagement programs. You can see on the screen being shared right now, you can see the rough agenda for today's meeting. This meeting features a webinar presentation on the 10-year review of the I-35W bridge instrumentation and data interpretation. Following the presentation, we will hear from staff at the MnDOT Bridge Office on what they've learned from this research. And we will also have a round-robin sharing from all of you. I'll turn it over to Gina Bass, Associate Director at CTS, who will share a few housekeeping items and then move us on to a time of recognizing Carol Shield for all of her contributions to CTS.
Great, thank you, Mark. Good morning, everyone. It's a pleasure to have you here with us this morning for this council meeting and the webinar on the I-35W bridge. So great to have all of you with us today. So just a reminder that if you have a question for or a comment for the speakers during the presentations, please use the Q&A feature for those, and we will share those during that time. You're also able during the chat or during the round robin time to use the chat by connecting or by hitting all panelists and attendees, and we'll verbally then can share those round robins. If you have any technical issues, Katie Kirk is going to be monitoring, and you can contact her directly or privately if you need to through chat if you're having some technical difficulties. And then we did want to remind this group that you know, you are able to count today's, to the best of our knowledge, I have to say that for the professional engineering group, but to the best of our knowledge, you are able to use the today's webinar as a 1.5 PDH's credit. So if you need the form, send Katie a direct message through chat, and she'll with your email address, and she'll get you what you need. So it's my kind of bittersweet pleasure now to just say a few words of thanks to Carol Shield. So little did we know that when CTS awarded her the Braun Distinguished Service Award back in February that Carol was going to announce that she was retiring from the university effective this September. So thankfully, that was serendipitous, and we were able to recognize Carol for the many years of service that she has brought to the university, but also to MnDOT and the state of Minnesota. So we really appreciate everything she's done. And as we had noted back then, Carol has worked on over 30 research projects. I'm sure it's many, many more. Those are the ones that CTS is aware of anyway, since she joined the university back in 1991, and has just been a great supporter for CTS, which we have greatly appreciated, as well as a longstanding and active member of this council. And so it's with a little bit of regret, but also happiness for Carol that she's moving into this next phase of her life that we say congratulations and best wishes. And Carol, if you'd like to say a few words, that would be great.
Thank you very much, Gina. Those are very kind words. I just thought I'd tell a little story that when I started back in 1991, a lot of people don't know this, but I don't have any degrees in civil engineering, and I didn't know anything at all about bridges. And I unintentionally ended up in a civil engineering department, and I can remember Kathy French saying to me the first year, "Oh, you should put in a MnDOT proposal." And I was thinking, I don't know anything about bridges. Why would I want to do that? And a few years later, as you mentioned, I think 30 some projects, 7 PhDs, 22 MS theses, 3 partnership awards, lots of bridges instrumented and monitored. I now feel like I know a little bit about bridges. And I would like to thank CTS, because I don't think that I would have gotten into all of that without the help and the support from CTS, and the friendships I've gotten there and the help that's come from CTS has just been fantastic. And yeah, I'm happy to be moving on, but I will definitely miss a lot of what I was doing. So thanks again, Gina.
Great, thank you, Carol. And I think that sends it back to you, Mark.
Thank you, Gina. Well done, Carol. Well done. This slide will show you some upcoming CTS Research Council webinars, and I wanted to point out that these are free, but you do need to register in advance for them. You can see the 3 topics that are coming up yet this year, yet this month: the innovative strategies for last-minute delivery in urban areas, the exploring a smart cloud commuting service, and how transportation can help reduce Minnesota's carbon footprint. So please look into those, and as I said, they're free, but you do need to register for them. I also wanted to point out that this year's CTS Transportation Research Conference that is held every year will be held this year, but it will be virtual, and you can see the date and time there. It does have a $40 registration fee, but you have till the end of October to register for that. You can see the link on the screen, and if you just go to CTS, you can find your way to it as well if you haven't gotten any advance notice of it. I'll move on to the our main topic here today, and that has to do with the 35W bridge. I want to say the 35W St. Anthony Falls Bridge includes instrumentation for the long-term monitoring of the bridge's structural behavior. This long-term deployment of over 500 sensors offers insight on monitoring of bridges and unique data set to investigate structural behavior. The presentation will introduce the monitoring system and highlight key results related to temperature-dependent and long-term time-dependent behavior. Giving this presentation today is Lauren Linderman. Lauren is an assistant professor for the Department of Civil, Environmental, and Geoengineering at the University of Minnesota. Her research is focused on cyber-physical systems to improve the long-term performance of structures or limit their response during transient events, such as earthquakes. Her primary areas of interest include vibration mitigation strategies, decentralized control, wireless sensor systems, and data acquisition techniques. Dr. Linderman?
Well, thank you very much. So I hope everyone can see the slides.
Hi, Lauren. I think this is Katie. I think that's the presenter view currently being displayed.
Thank you.
There you go. Perfect.
Thank you. I thought I'd fixed it. Okay. So it's my pleasure to talk today about a project that we've been working on, or just completed, related to the 10-year review of the I-35W bridge, particularly the instrumentation and data interpretation. And so we reviewed the instrumentation performance and then expanded on some of the previous work on the time-dependent and temperature-dependent analysis from the data. And so the work today that I'm presenting is a culmination of lots of people's contributions. So this is not just my work, but from many people. And so we had a significant number of researchers, faculty, and students that worked on this project, as well as collaborators from MnDOT. And so I just want to acknowledge them before I get started today. And I'm particularly going to highlight the both researchers that were on this version of the project. So Carol Shield, who we just acknowledged, Professor Brock Hedegaard at University of Minnesota Duluth, and then Riley Brown, who recently graduated with his master's, and Rebecca McCoy, a current master's student. So the work I'm presenting today isn't mine alone, but from many. So I'm going to start with a background on the bridge and present a little bit more about the actual instrumentation and focus on the key instruments that I'm going to touch on in this presentation. And then for the researcher outcomes, I'm going to focus on our understandings that came out for both the temperature dependent behavior of the structure and the time dependent behavior, because I think this made some pretty unique contributions to some of the design assumptions that we use. And then also discuss some lessons learned, and I hope that MnDOT can touch on that as well after the talk. So the I-35W St. Anthony Falls Bridge opened in September 2008. And as part of the bridge project, it was designated as a smart bridge. So it contains over 500 sensors that were used to investigate behavior. So these include strain gauges, temperature sensors, corrosion sensors, fiber optics for strain, linear potentiometers for evaluating displacements, and accelerometers. And the goals of the instrumentation were to evaluate design assumptions, investigate structural characteristics and potential changes over time, as well as evaluating the effectiveness and appropriateness of the selected instrumentation. So a little bit about the bridge. So the bridge is actually, there are two separate bridges, a northbound and a southbound, that are almost identical. They are each with two boxes, and there's 3 continuous spans and then an additional span. This continuous part is about 1,200 feet and the 500 feet river span. They're post-tension concrete box girders, with each bridge consisting of 2 single cell boxes that are post-tension together to make up the section. And so the main span was constructed using precast segments, while the other spans were constructed using cast in place on falsework. As you notice, the cross-section is deeper towards the piers and gets narrower towards midspan. And most of what I'm going to discuss today is going to focus on the river span, and then also looking at the kind of along the length over these first three spans. So here you can see the bridge instrumentation pictorially. And so most of the instrumentation is located in the southbound structure. We decided to heavily instrument one structure, and then there's some parallel instrumentation in the northbound structure to see if things are performing in a similar manner. There's LPs, which measure displacement, located over the bearings or the joints. There are accelerometers placed throughout the structure, as well as vibrating wire strain gauges embedded in the concrete to measure strain. And they also provide temperature information. There's additional thermistors at the midspan of the river span, and then there's fiber optic strain gauges placed along the length of the southbound structure. And so I'm going to emphasize or discuss a little more detail the vibrating wire strain gauges, the thermistors, the fiber optic sensors, and the LPs, which measure displacement, because you'll see more information related to that data in the remainder of the talk. So there are 147 vibrating wire strain gauges used in the bridge superstructure. 112 are in the southbound bridge, and 35 are in the northbound bridge. These are cast mostly within the concrete. They're approximately 6 inches long, and they measure local strain. They also include a thermistor, so they allow us to measure temperature as well. And we use these sensor information to look at load distribution, shear and torsion, deformation, and then curvature along the cross section. So typically these are placed through a cross section, and so we can get a distribution of strain. So what I've highlighted here are the key cross sections that are instrumented along the length of the bridge. And in addition to the thermistors available in the vibrating wire strain gauges, there's 48 additional thermistors in the bridge superstructure. Of these, 42 are installed in the southbound bridge. So these were used to supplement some of the data from the vibrating wire strain gauges. So here I show one of the cross sections at mid-span of the southbound structure. There's vibrating wire strain gauges distributed along the depth. And then there's an additional set of thermistors, an array here, that are included to understand the distribution of temperature through the flange of the box. And we used the additional temperature information to look at thermal gradients through the cross section. Each box at the bridge expansion joints include a linear potentiometer. So this is used to measure the displacement of the expansion joint, or the overall longitudinal movement of the bridge. And these are used, these are kind of the majority of what we use for the long-term analysis to look at the overall global behavior of the structure. Okay. And then finally, for the fiber optic sensors, these are strain gauges that are located in 6 sections of the river span. The sensors measure average strain. So the sensors are about 13 feet long. And so the strain is averaged over that distance, unlike the vibrating wire strain gauges that measure more local strain. And so we have an average strain at the top and the bottom of the cross section. And so we use that to look at curvature. Overall in the project, we found that the instrumentation survival rate is about 90%. This is significant given the duration, the number of sensors, and the embedment of a lot of these gauges. Some instrumentations performed better than others. So we had to replace several of the linear potentiometers, and the corrosion sensing system never functioned. So that 90% is kind of distributed on average, while some perform better than others. And the temperature sensing, the strain gauges, the linear potentiometers, and the accelerometers, as well as the SOFO systems, mainly were used to validate design assumptions, provide insight on the temperature and time-dependent behavior, and then also calibrate the FEM model that I'll discuss in a moment. And of particular interest, the temperature measurements and the displacement measurements at the joints, these have been essential for long-term monitoring of the structure. And so these are kind of the key measurements that we've been building off of. So in general, with any monitoring system, the goal ideally would be to take our measurements and then be able to identify structural changes over time to provide some insight of where to look or things that might be of concern. And that sounds pretty straightforward, but it's not. So what you can imagine is, let's say I'm taking measurements from the bridge. That's going to be this black line here. So this is the displacement reading at one of the expansion joints over a 9-year period or 10-year period. And so what you'll notice is there's large seasonal variation, and what looks like noise is actually daily variation. And so this kind of natural, safe variation can often mask any anomalous behavior. So what I would actually be interested in is this kind of backbone curve that represents the time-dependent behavior of the structure. So this would tell me if like creep and shrinkage are undergoing as expected, and if there's any large changes in that area. And so the idea is, how do I go from this kind of really noisy data, or what we think is noise, to actually identifying what's changing with time? And so data from individual sensors alone isn't going to be able to do that, because if I just had a sensor alone, then I just had this kind of bearing displacement data. And so some of the challenges of doing this is that bridge behavior depends on a lot of complex phenomena. And what we're trying to use is data from a group of sensors through a cross-section, particularly temperature in addition to mechanical measurements, in order to identify the actual baseline behavior that we're looking for. So for this structure, we took the measurements and then looked at some of the key behaviors. So we have both time-dependent behavior and thermal behavior that are going to be driving behavior of this structure, and combine that with an FEM model, which is informed by a dynamic model and some of our measurements, as well as information provided by truck tests, so that we can ultimately identify structural changes over time. And what's interesting, or kind of nice too, is that these thermal behavior and time-dependent behavior analyses that we do help us evaluate some of the design assumptions that were used for constructing this bridge. And so today I'm going to focus on the thermal behavior and the time-dependent behavior, and how that kind of informs the longitudinal displacement. And so this uniquely large data set allows us to evaluate these design assumptions, and understanding these are going to be essential to investigating structural characteristics and potential changes over time. And then, as I mentioned, this also allowed us to evaluate the effectiveness or the appropriateness of the selected instrumentation. So the first thing I'm going to touch on are the temperature response of the structure. And as you can imagine, in Minnesota, the temperature loading can be quite significant. Okay. So often when we think about temperature loading, what we're actually thinking about is thermal gradients. And this is the temperature variation through the cross-section. And this is going to cause thermal stresses. So what you're looking at here is a combination of vibrating wire strain gauge and SOFO measurements along the length of the structure. So here's the location. So this is Pier 2 and Pier 3. This is the main river span. And what you see on this axis is the curvature. And what we're showing on the, what we're showing on the left is the curvature induced by a truck test. So we had 8 fully loaded trucks sitting at mid-span, and here is the induced curvature due to that loading. And on the right, you see the curvature or strain due to the thermal stresses due to one of the large positive thermal gradients. So the top of the bridge is warmer than the bottom of the bridge, and this is going to introduce thermal stresses. And what you can see is that the curvature induced by the large positive thermal gradient actually has significantly more curvature as a response than due to the fully loaded trucks. And so the thermal effects can actually be quite significant on this structure. And so what we're going to look at is what are the shapes of these thermal gradients and how do they compare to what we imagined for or proposed in design. So what we're looking at here is the thermal gradients through the cross section. So we're looking at the temperature through the cross section. So here's the depth of the cross section. And so, and here are the temperatures. And so on the left, we have the positive gradient where the deck is warmer at the top than the bottom of the bridge. And on the right, we have the negative gradients where we're cooler at the top than the bottom of the bridge. And we're looking through one of the webs of the box at midspan. Okay. And what you'll notice, I have here plotted the 5 worst gradients that we captured in comparison to design thermal gradients. They're a little hard to see when we look at the full profile, so I'm going to zoom in and look at the area above or within the flange of the box. And so what you have here, this is the AASHTO design curve. These are the measured data points, and this other dashed line is going to be the Priestley New Zealand curve. And then on the right, you see the negative gradient profile. In both of these, what you'll notice is that the New Zealand curves that are scaled to the same region that we're in, AASHTO Zone 2, better approximate the maximum measured thermal gradients than AASHTO. So when we're worried about thermal gradients, we're interested in kind of this area back here. And so by aligning with here, we're going to have a larger thermal gradient magnitude. And we see that both in the positive and the negative gradients. So the gradients are larger, but what impact does that actually have? And so we looked at the induced stresses by applying these thermal gradients to the previously kind of confirmed 2D finite element model to compare the effects of the thermal gradient. And so what you're seeing here are the stresses derived from that along the depth of the cross section and compared to the code. And we found that typically the measured stresses were best matched on average by the Priestley New Zealand prediction. And this causes additional tensile stresses due to the gradient. So they're about 80% larger at the bottom fiber due to positive gradient. And then the top fiber, negative gradient, tensile stresses are about 30% larger. And this could be significant for serviceability. So what we're concerned about is if you have larger, sorry, distracted by the chat. If you have larger tensile stresses, you could get cracking or unanticipated cracking. So we see that it is possible that these large gradients could induce large stresses. But the question is, like, how often does this actually happen? So I only showed 5 of the larger gradients. Is this going to be a common occurrence? And so what we looked at were the measured positive gradient magnitudes compared to design gradient magnitudes. And so here you see the measured gradients over time. And these 2 lines here that I've highlighted are the AASHTO LRFD magnitude and the Priestley New Zealand magnitude. And what you'll notice, at least for the positive gradients, is that there's a significant seasonal variation. So you get larger positive gradients in the summer and smaller in the winter. And you see this when we look at just the number of days per month where we're exceeding the AASHTO design magnitude. And so we typically exceed the AASHTO LRFD design gradient on 33 days per year, so it's pretty consistent. And we only exceeded the Priestley design gradient 3 times over the 9-year period. Okay. And we'll see kind of a similar rate of exceedance when we look at negative gradient magnitudes, but these aren't going to have that same seasonal dependence that we saw with the positive gradients. So we tend to have large measured negative gradients throughout the year. And what you're going to notice is that we often exceed the AASHTO LRFD design. And we're actually also going to exceed the New Zealand gradient more frequently. And so on average, we exceed the AASHTO LRFD design gradient about 54 days per year, and we exceeded the New Zealand design gradient on average 2 days a year. Okay. So one thing that's kind of interesting is, okay, so we have these thermal gradient stresses, but that's usually not the only thing that's on the bridge. So how does this actually impact our service load stresses, or what we might consider for design? And so what we looked at was the impact of the gradients on these service load stresses, where our concern is cracking rather than strength. And so here I have the relevant service load combinations from AASHTO LRFD. And so we have some combination of our dead load plus post-tensioning plus creep and shrinkage. And then the difference in the combinations is going to be how they combine live load and our thermal gradients. And so you can have some live load on the structure and then some different variation on the thermal gradient. And service 1 or 3 would be there's no live load and full thermal gradient. And what we were interested in was kind of the tensile forces, and particularly we focused on the tension in the top flange due to negative thermal gradient. So you are worried about cracking in the deck. And we looked at 3 different models for the time-dependent behavior. So we could look at kind of what we think might be happening versus what would be the design expectation, and how do we compare. And so we combined the top flange tensile stresses. So you have the stresses through the cross-section due to the dead load, post-tensioning, creep and shrinkage, additional stresses due to live load, uniform temperature, and then your thermal gradient, and you get a total stress. And what I'm in the table below is just the top flange, so just this upper red line under negative gradient at midspan. And we're comparing that to the min dot tensile limit that actually enforces that the top of the deck should still be in compression due to the post-tensioning to limit the potential for cracking in the deck. So we looked at different creep models. And this structure was actually designed for CEB 1978. And then different temperature gradients that could be used. And what we're interested in here is this total number. And so if you had CEB 1978, you design it for AASHTO, you'd expect that you're getting about 500 strain and compression. And so that is significantly lower than your tensile limit. But what might actually be happening on the bridge might be closer to one of the CEB 1990, and then measured one in New Zealand, or closer to the thermal gradients that we're actually seeing in the structure. And if that's the case, you're getting about a 300 microstrain in compression. So you're still not going close to that tensile limit, but you have about 200 more strain in tension than you expect. So as a designer, if you are actually looking at a tensile limit of 0, you might be going, you might actually have unanticipated tensile stresses in the deck due to this kind of unconservative assumption of the negative thermal gradient in the region. And so this could inform kind of future work on thermal gradients, particularly for Minnesota, and how you would consider these in your design. Okay. The next thing I want to touch on is time-dependent deformation. And so there's conflicting time-dependent models that predict disparate displacements due to creep and shrinkage. And so the I-35 data set allowed for measured time-dependent deflections and strains to be determined. And then we could compare these with existing models under realistic volume to surface ratios and temperature histories. And the reason this was of interest is that long-term creep and shrinkage could potentially lead to post-tensioning losses. And so what we're showing here is just an example of the different creep and shrinkage models. So you have an applied load, you get your initial elastic strain, and then that will creep. And there's 2 main types of models, logarithmic models and then asymptotic models that have slightly different asymptotes and different rates. Okay. And so in order to identify the time-dependent deformations, we need to take data that looks something like this, where we have the temperature variation, and then look at what we ultimately want to see, which is the time-dependent deformation here in red. And so to do that, we're going to use some data normalization techniques. And the first one, or first part of that data normalization, is to extract the temperature effects. And so we have our measured data, and we know that should be a combination of the temperature effects, the time-dependent behavior, and then we're going to have some error. And so we're given our measured data and our temperature, and we're going to do a regression of the data to remove the temperature components by calculating these coefficients, so that we should be left with just the time-dependent behavior. So we assume a time-dependent behavior model, computer coefficients using a regression technique, and then remove that component. Okay. And there's usually some remaining temperature effects that may be not modeled in this kind of error residual. So when we get out is going to be what's on the left. So you have your data normalization adjusted for temperature, and then this is compared to actual time. And what you'll notice is that creep is going to increase when it's warm and slow down when it's cool. And so you get temperature dependent rates of concrete aging, creep, and shrinkage. And if we want to compare these to any sort of model results, we're going to compare them to a model that's computed at a constant temperature. And so in order to make these comparisons, we use an adjusted age. So we pull everything back to the same constant reference temperature to account for this kind of increase when it's warm and slow down when it's cool. And so this will allow us for comparison with creep and shrinkage predictions, so we can get a better idea of what model is most effective. And so you go from something like this to looking at the time-dependent behavior as a function of what's called adjusted age. And so what you see here is the bearing displacements on the northbound structure at the two different joints, and then total time-dependent behavior of the entire three spans. Okay. And so we took that time-dependent behavior and compared it with FEM predictions. And what I'm showing here is the displacements measured at Pier 4. So a positive longitudinal deflection actually corresponds to the bridge shortening. And we're looking at the measured data here versus different models over adjusted age. And we're still kind of early in the life of the structure, but as you can see, if I zoom in, the bridge is creeping and it's starting to slow down. Okay, and we can compare that with models applied to the FEM predictions. And what we notice is that the CEB FIP 1990 offers kind of a conservative assumption of the behavior. And we're getting more creep and shrinkage that would be anticipated by ACI 209 or AASHTO. And so in general, we found that the CEB 1990 and ACI 209 kind of offered the best approximation of the time-dependent behavior in the structure. Okay. And then this longitudinal deflection was ultimately used to look at the long-term performance as part of our monitoring project, where we've computed both a short-term check and a long-term check to detect anomalies. So the first is to just look at short-term changes, something like a bearing lockup, and the second was to look at how overall the time-dependent behavior might be changing. And for that, we looked at the slope of the time-dependent behavior, and it should always be decreasing and positive. So the bridge should always be shrinking. So what lessons did we learn from this? So the key one, I think, is that the environmental factors are essential to interpreting structural behavior. And as a result, we would propose that you would want more than one heavily instrumented cross-section. So this would allow you to capture temperature distribution throughout the structure as the cross-section changes. So instead of having a very heavily instrumented single cross-section, kind of have more cross-sections with a better distribution of sensors. This long-term data set also allows us to isolate normal variations. And these normal variations actually help us evaluate design assumptions. And then we did find that one thing to be aware of is that there are challenges when accounting for system outages when you're looking at long-term behavior. So how do you connect disparate data if you have an outage over a period of time? And then more directly related to kind of instrumentation and how you would deploy the system, our kind of belief is that experts should be present during the installation of sensors along with the construction team to collect data at appropriate times, and then also document the exact location and orientation, which improves instrument or interpretation of the results. Also, it's key to protect sensors or wiring and labeling during construction so that you don't kind of lose any sensors in the process. And then also, when you're doing your system design, kind of think about the robustness to component failure. So if you lose some component, is the entire system going to be down? Or how are you robust to things like electronics outages due to lightning strikes? And then finally, evaluate the sensitivity of the sensors when you select them to make sure that you're actually obtaining the behaviors of interest in the system. So I want to thank you for your time today. So that was kind of a lot. And again, acknowledge the collaborators on this project. So again, this is not my work alone. And I think Carol has been helping to answer some of these questions. And this work has been included as a few different reports. And then there's the most recent report that came out with related to the 10-year review. So thank you again.
Well, thank you, Lauren. A great presentation, and thank you for your lessons learned that answered some questions that I personally was going to put in the chat. And speaking of, Christy, are there any questions that are appropriate for Dr. Linderman to address at this point, or should we be moving on?
There's a few questions we can touch on. I know they're written in the chat and Carol did provide some responses, but it might be nice just to hear those responses out loud as well. So there was an initial question about how many trucks were involved in the measurement of truck-induced stresses and strains. And it sounds like there were 8 fully loaded sand trucks. I'm curious, do you guys have the approximate weight of each truck?
I don't know that off the top of my head. I don't know if Carol does.
I think they're about 50,000 pounds.
Okay.
Okay.
Each.
So then there was a supplemental question to that. What is the impact of increasing the number of trucks on the reported stresses and strains?
So it should be linear. And I guess the 8 trucks we moved throughout locations on the bridge. And what I was presenting was just one instance where they were as close as possible together at mid-span of the river span. And as Carol pointed out, this live load is going to be larger than you would ever locally have that you consider in the design loads.
And then we have another supplemental question. Does it imply that the truck-induced stresses, strains can exceed the temperature-induced ones if the number of trucks is higher than 8?
And so I agree with Carol that I don't think you would ever, under normal circumstances, get traffic-induced curvatures larger than thermally induced. So I don't think you would ever see a distribution of loading that would cause that to happen, since these were definitely over the legal limit of load.
And then we do have a question. Does the sensor data include signatures of structure deterioration, such as cracks or fatigue?
So this bridge is still very new, so we haven't seen any signatures in the structure or in the data due to any sort of deterioration of the structure as of now. So we haven't noticed any signatures of cracks or anything of that nature.
Great. So Mark, did you want to introduce the MnDOT folks, and then we can take any more questions that the group has?
Great, yeah, I'll do that. Thank you, Christy. You'll note that Dr. Linderman had noted that this project was a collaboration, and in addition to Carol Shield, there were some MnDOT employees, representatives that were involved with this project, and I'll give introductions for those people. Ben Jilk is the complex analysis and modeling engineer for the Minnesota DOT Bridge Office. He holds a master's degree from the U of M, where his graduate work involved the initial project for instrumenting the new 35W bridge. He has since served as the MnDOT technical liaison for all of the research projects involving the new I-35W bridge. We also have with us today Dwayne Green. He's been a bridge structural engineer for 47 years and received his Bachelor of Science degree from the University of Illinois and a master's degree from the University of Missouri. Dwayne joined MnDOT's bridge office in 1998 as a bridge design engineer and transferred to MnDOT's Metro Maintenance Division in 2008. Dwayne is currently Metro District Structures Maintenance Operations Engineer. So I believe, Ben, you want to get us started?
Thanks, Mark. Lauren touched on a lot of things we learned on this project, but overall from MnDOT's perspective, the research done on the 35W has been a success. We achieved the goals that we set out to reach by installing instruments on this bridge. Of the more important things, we did confirm that the design of this bridge is conservative, so that's always a good thing. In regards to the design, the results that Lauren was talking about, thermal effects and time-dependent effects, were interesting for us to see. The time-dependent effects, the CEB FIP 1978 code was used for the design of the 35W bridge. And from what the research has shown, that was a conservative assumption. Our more recent segmental boxes in Minnesota have used the 1990 code, which is the code that actually correlates better with what the research has shown, what the behavior of the 35W has experienced. Again, as Lauren mentioned, the thermal gradients exceeded those specified in AASHTO for our region. When included in load combinations, this can actually exceed the limits allowed in AASHTO. But fortunately for Minnesota, we've had more stringent restrictions on our stresses. So even with this exceedance of AASHTO, we still stay within the limits that AASHTO would allow. So these things have given us confidence that the design criteria that we've used on our major projects like 35W has been appropriate. In addition to the knowledge gained about the design of segmental box girders in Minnesota, we also learned more about the different sensor systems. Lauren touched on a lot of this stuff. First, getting researchers on board early is important so that they can start planning on where they might need instruments and have time to think about that to get the behaviors of interest that you're interested in. We also found having researchers involved is important, since DOTs generally don't have the time or the experience or expertise needed to be able to evaluate the sensor data. In the case of, for us with 35W, having the University of Minnesota involved has been really great. They've really cared about what might interest us and what things we might want to see. And they've also done a great job of helping keeping the system up and running, because we've had electrical outages due to lightning strikes, and they'll get in there and they'll fix things up for us and let us know that things need to be fixed. Lauren touched on needing to make sure that instruments are protected during installation and construction. We did have an issue where some of the cables and some of the instruments that were in the pier got cut off, so we no longer knew where the which gauge the cables were connected to. So some of that data becomes essentially useless if you don't know which sensor it's attached to. So in the future, trying to implement more strategies to try and protect these wires and the labeling so that you don't lose sensor data is important. Overall, we had good success with the sensors, but we did find that some did not meet expectations or did not provide additional information over other sensors that we would want to use them again. So for example, the corrosion monitoring sensors never really worked for us, so we didn't get good data out of them, and we wouldn't implement those on a bridge in the future. I think Lauren touched on the other things that we learned in terms of sensors. So as far as future research goes, we don't currently have any more plans for further research on this bridge, but we would like to continue to collect data and potentially look at this data in the future. Again, maybe another 10 years, or I don't know when the time would be, but to possibly look at where creep is, the time-dependent effects are in the future, and see how that's trending with the different codes. So with the 1990 CEB FIP code. And information gathered from this research will most likely be implemented on future designs of segmental boxes or other similar structures in Minnesota, particularly the thermal gradients, and trying to get a more appropriate thermal gradient included in the design. With that, I'll pass it off to Dwayne if he has anything to add. Otherwise, we can hand it off back to you, Mark.
This is Dwayne Green. I guess I really don't have much to add to what Ben just covered. I will, for future research projects, I do want to highlight the fact that to consider natural weather effects. We had a lot of issues with electrical lightning storms on these major bridges, and burning out circuit boards and that, even though the system was well grounded, but things like that happen, and to have some sort of a plan on how to get there easily and fix that stuff is something to keep in mind. He also mentioned the corrosion resistance was something that we were really looking forward to trying to get some data from, and it didn't pan out for us. So again, it's that maintenance type work at the end of your systems to keep that in your thought process when you're coming up with the monitoring systems and the location for your gauges. With that, I'll pass it on.
Well, thank you, Ben and Dwayne. Christy, do we still have questions that are coming in to the QA or in the chat box?
Let me just look through here. I think we just have a new one that popped up. So we have a question: how long will the monitoring take place? And then what arrangements have been put in place to collect and review data when everyone is gone 25 or 50 years from now?
I don't know that we've had specific discussions for that far out right now. Right now, we're trying to find ways to include continuing monitoring, collecting the data. So we'll continue collecting the data. It's automatically collected on the computer attached to the bridge, so it should be able to continue collecting that data on its own. And we get emails letting us know that the system is out, so we know when we need to go in and fix something so that it does continue to collect data. But 50 years from now, I can't say that I know right now.
Well, what is the service life of that bridge? Is it like 100-year?
It should be 100-year.
Okay. Do you know what the typical service life of a sensor is on the bridge?
I think that's a better question for Lauren or Carol, probably.
So I don't know the actual service life of some of the embedded sensors, like the vibrating wire string gauges. They've continued to operate quite well. I think the bigger issue are the sensors exposed to the environment, so things like the linear potentiometers, and then also the service life of the actual computer hardware that's used to collect the data, I think is more of an issue than the actual sensors out on the structure. So the server life or the computer life, I think is a bigger issue than the life of the sensors themselves. Some gauges are designed to be used long-term. So for example, a vibrating wire string gauge should last longer than, for example, like a foil or kind of a wire resistance gauge that is really short-lived. But I think, yeah, the bigger issue is the maintenance of the actual data acquisition components.
So I had a question. I was curious, are you able to use any of the data from the monitoring system for the required annual or biannual condition or structural inspections of the bridge?
We don't use it to replace any normal inspections. I don't think it was ever intended that it fully would. We were hoping the corrosion monitoring sensors would give us additional information, or the some of the linear potentiometers measuring the openings at the end of the bridge. If we get some weird reading, it might give us an indication that, hey, you should go look at this, but it won't be used to fully replace our normal inspections.
Okay. Another question, what new instrumentation protocols were developed on this bridge, and has it established any new standards?
So I guess I can take a stab at this and then maybe send it over to Ben. So I don't believe we've actually worked this into any new standards. We've been kind of reporting on this work, and I think it's been of interest to at least the monitoring community of how you can deploy kind of long-term instrumentation, what is key instrumentation. And I think there's still some thought of like how some of these findings related to thermal gradients might be able to work their way into kind of design practice, but no new standards have actually been developed as of yet.
And I agree with Lauren that, you know, we don't instrument a lot of bridges like we did this one. If we were to instrument something in the future, it would give us a lot better idea on what type of instrumentation we might need to do, but there's no actual standard or policy that's been developed. As far as the thermal gradient piece, we'll be looking at that further. Certainly it looks like something needs to be considered in Minnesota, but it's hard to say as far as AASHTO as a whole, if it needs to be implemented, because Minnesota compared to the rest of the country, it may not look the same. It may not be exceeding AASHTO values in other parts of the country.
So I have a few more questions. What was the estimated cost at the time of installation? I assume that's for the sensoring monitoring system.
I don't have that number off the top of my head.
Has MnDOT placed any similar monitoring equipment on bridges that are similar to 35W, such as maybe the Winona or Dresbach Bridge?
No, we have not. We've used instruments on other bridges, but not nearly as heavily as 35W and not long-term like 35W, and nothing of a similar type.
Are there any other potential bridges in mind for similar installation in the future?
I think where we might see some potential for instrumentation would be on some existing bridges if we want to look at how they're behaving, and for like load rating purposes, make sure that everything's okay. But new bridges, I don't foresee anything like this.
So we have a question. How does the I-35W bridge sensor data analysis compare with those from other instrumented bridges in the US or abroad?
So I guess I can touch on that. So my understanding is that this is kind of the longest bridge instrumentation project in the country. So in terms of like a continuous monitoring system, this is a pretty unique opportunity that we actually have 10 years of data. They typically tend to be shorter term deployments. And then in terms of the sensors, these are wired kind of embedded sensors. It's unique to have a new structure with a lot of embedded sensors in the concrete themselves. So that's kind of unique. In terms of like globally, I don't know. I know other countries also have instrumented structures, but I think in the US to have a new structure instrumented like this is pretty unusual. And then I know some of the data analysis where we're actually looking at time dependent and temperature dependent behavior on site. It's one of the few projects that we're seeing this data start to appear.
Well, thanks for the questions, everybody. If you have any further questions, feel free to type them either in the Q&A or the chat feature. And thanks, Ben and Lauren, for answering those questions.
Thanks.
Also, we do a round robin at the end of the meeting. So if you have any announcements or information you want to share about your organization, feel free to type that in the chat box as well, and I can share that with the group. Also, if you have any ideas for future presentations that this council might present on in the future. And also just to note that this webinar is being recorded and it will be posted online for people to watch after if there's others in your organization that are interested.
Hi, Christy, this is Gina. So this is challenging to do the update in this manner as we know. So, if there are, folks from like other researchers that are on the call, if there are projects that you might just want to briefly mention and highlight, that would be great. And then for folks that are from agencies or from agencies or from consulting firms, again, if you've got interesting projects that you might want to share an update on, we'd love to hear about them.
Well, Gina, I think we were expecting to use the chat function for people to share things, but I'm going to use my platform here to raise a topic of a possible research interest that maybe this audience today is not the perfect audience for it, but I do know that local governments in this market and probably in other markets, but especially in Minnesota, are very interested in is traffic behavior information in light of the fact, and especially on lower volume roadways, in light of the fact that there's been a great deal of e-commerce and people buying things and having it delivered. And we're seeing there's a lot of people who are interested in some possible changes in the characteristics and the mix of traffic in residential areas. And that's being compounded because in Minnesota, maybe a lot of people might not be aware that the state's legislature allowed local governments to change speed limits. And so now you couple the speed limit topic with the possible mix or changes in mix of traffic in residential areas. And a lot of the people that do what I do for a living, which is local government traffic management, are trying to establish what might be going on and what the trends are in residential streets. And so I'm just getting that out there everywhere that I have an audience right now that where people might be in the research world. So just for what it's worth.
Well, Mark, I know that next week's Planning and Economy Council meeting is going to talk a little bit about e-commerce. So Ali Reza Khani from Civil, Environmental, and Geoengineering is starting a project related to that. I don't know that he's looking at traffic impact. So I think that that's a great point, that that might be an element that, I mean, again, you know, I think in general he's probably going to be looking at amount of vehicles, but additional, you know, looking at the traffic impacts beyond that, I'm not sure if that's the case. So it's something that, you know, to maybe build on the work that he has just started. And then he has a colleague from, I believe it's Portland State, that is also going to be presenting some work. So yeah, that's, you know, if you're able to tune in for next week's Planning and Economy Council meeting, I think they'll be looking at some of that, but as well. But I think you raise a good point of looking at the traffic impacts piece and how important that is.
Yeah, thank you, Gina. Have any other submissions or any other input?
We do not have anything at this time, so do we want to close out the webinar here? Or here we got something. There was just a note that an upcoming presentation is titled Identifying and Optimizing Electric Vehicle Corridor Charging Infrastructure for Medium and Heavy Duty Trucks.
Oh, I think that's actually the Energy and Environment Council meeting. So there are 3 more council meetings and webinars that are coming up in the next few weeks. So I think that one is focused on the Energy and Environment Council. The one I was talking about specifically related to e-commerce was the Planning and Economy Council. So another good plug for the upcoming webinar. So that's great.
And I'm seeing that in the chat box that the information, the link has been provided for that. Anything else, Christy, showing up?
There is not.
Okay, well,
a quiet bunch.
Well, I did see a comment just come through in the box. I don't know if that was.
Oh, here we have another question here. Much of the success of the I-35 bridge can be attributed to all parties following an ideology called vested, especially the expedited timeline. Does MnDOT consider using this model on current projects?
I guess I'm not sure I've never heard of vested before. So I can't comment on that.
Okay. Anything else showing up, Christy?
No, Mark, there's nothing else at the moment. Here it says it has been documented in a white paper found on vestedway.com and in a book.
Well, maybe that's all our homework assignment is everybody can check it out and see what that is.
Okay. Okay, well, I think we are nearing the end. Check the chat box and look for the links for the research projects that were mentioned. I wanted to, again, congratulate Carol Shield and say thank you, a great thank you to our presenters today, Dr. Linderman, Ben Jilk, and Dwayne Green. And with that, I think we're complete. So thank you all. Audience, thank you for participating, great questions, and watch the links for future upcoming webinars and the Transportation Research Conference. Thank you all.
Great, thank you.
Thank you.
Thank you.
Thanks.